Hello, hello. Today will not be a very long day in terms of teaching. I also have the world's best video to show you guys. World's best video. No problem. Yeah, it's hilarious. So, if you were reading the paper that you got when you came in, it's a song, but if you notice it's about, at the end, entropy, right? You don't know what entropy is yet. Does anybody really know what entropy is? Okay, next. Alright, so that's what we're going to be doing today. I might show you more in another video of explaining entropy, but that's at the end of the bell. Okay? Sound good?
No.
So let's go ahead and begin. You should be in the slides with us. We're going over the steps of a refrigerator. How cool is that? The reason why we're doing this is because this is the total opposite of a heat engine. Okay? A heat engine, if you recall, since it's the opposite of this, and this is doing work, or using work to do heat, a heat engine uses heat to do work. The example that we had for that was a combustion engine, where we use the combustion reaction, use that heat to move that piston and turn the crankshaft. Okay? That's what the combustion engine did. It was a heat engine. The opposite is the refrigerator, where you're using work to do heat. Okay? Because obviously in a refrigerator, you want to change the heat of the inside of the refrigerator. That's the goal of the refrigerator. Okay? So we're going to go through how this works. What you need to think of as the system, in this case, is the refrigerant. The refrigerant is the little diagram. The refrigerant is this liquid that turns into a gas and then becomes the liquid again. Okay? That is the system. The environment is anything that interacts with. So it interacts, as you see here, I'm saying it interacts inside of the refrigerator. So inside where everything's cold. It also interacts with the environment outside of that refrigerator. Okay? So it interacts with the environment in both. And you're going to see how the transfer of energy takes place throughout. So we're going to start at essentially D, around here, on the bottom, okay? And I'm going to kind of explain what's going on. Okay, so the refrigerant in your refrigerator and freezer, okay, they have a very low boiling and melting point. Okay? What does that mean to you? That means that it's going to be a liquid very easily at room temperature. It can also become a gas because a very low boiling point means that at very low temperatures it can boil. Okay? So, if you notice your refrigerator is really cold, it can boil inside of your refrigerator. Okay? Kind of bizarre, right? So that's what happens to the refrigerant. If you ever put in liquid nitrogen, that's similar. It turns into that gas.
Is that why the back or bottom of the refrigerator is too hot?
I'm going to explain why it's hot in a second. So, if we notice, we're going to start right here. This is a low pressure liquid, okay, at the very bottom. Low pressure liquid. And that's when it's going to start coming into that refrigerator. And then as it's going through the pipes, and when it's inside the refrigerator, what's going to happen is the energy, heat energy, from the refrigerator is going to be absorbed by the refrigerant. Okay? It's going to take in that energy from the actual environment of the refrigerator. When the refrigerant takes in that energy, what happens is a liquid becomes a gas, right? You take in energy and take in heat, you will change states, right? So it becomes a gas. So you have this gas right here going through the pipe. And when you heat up a gas, so when you take in more energy, what happens to a gas? Suppose I have a gas and then I add energy to it. What happens? It doesn't expand because volume is constant, but the pressure is going to go up. okay, the pressure will increase. Because if you think about, I won't relate it to work, but if you think about just water, it can become steam, right? That steam, when you heat up that steam, the molecules are going to be moving a lot quicker, right? That's what gases do, they move. And then as soon as you raise the temperature, those molecules are moving faster and faster and faster. Those interactions between molecules and between the whatever it touches, whether it be the table, so in the room, there's molecules, right? So those interactions are going to be pushing harder on those objects. Okay? Larger force, more pressure. Okay? So there's more pressure inside of this system. And we're at the very top right now. So this is a pressurized, there's a lot of pressure inside of this refrigerant, inside of this pipe. And then what we can do is we can condense that, so we even give it more pressure. When you condense something and give it even more pressure, what happens to the temperature? Unnecessarily, okay? It will increase and it will push out of the pipe. So what we're doing is we're condensing it and pushing it outward. Okay, this is essentially outside of the refrigerator, and this is inside the refrigerator. Okay, so to answer Brandon's question, this is why it's hot. Right here. Because we have a very high pressure gas. Okay, very hot because it took in all the energy from the refrigerator. And now you have a very warm gas going through a pipe. The environment now is cooler than the pipe. So thermodynamics tell us that that energy has to be released. Okay, it has to be released to that environment so that heat is going away at this point. Okay? And when the heat goes away, that gas comes back down and becomes a liquid. Okay? So, and then I'll finish it and then I'll kind of re-explain it. But when that becomes a liquid again, it's going to come back through the pipe. And, sorry, I didn't explain the work here, but I was saying. And then what's going to happen is that water, water does work, just so you know. If you ever have, I'm trying to think of the example, I'm missing it. Yeah, well, not like a water cycle, where water will push a
turbine.
Water will, I guess, I don't like it. What's that?
Turbine.
Yeah, it deals with the turbines, you can rotate stuff. Either way, water pressure can do work by pushing an instrument and making it turn, right? Okay? That's what I'm talking about here. That water pressure is going to do work on this little spigot down here. Right there. It's going to be doing work, that's why this work is going out on the environment. And then we're going to get a lower pressure liquid going into that actual refrigerator. Okay? So the same comes through, I can explain the work at the top. Because obviously you're doing work on the refrigerator, right? Because you're doing work to condense that gas at the top. Okay? So let's go through it. Stage A, we have a low pressure liquid. Low pressure liquid.
Wait, where are you?
Sorry, it's like right here. That's what I'm saying. Oh, we have a low pressure liquid, and what's happening is that it says evaporate. Okay, think of boiling, evaporation, right? As a low boiling point, so it's going to evaporate, if you will, or boil. Okay, become a gas. When it becomes a gas, then you're taking in more energy from the environment that's inside of the refrigerator. That's going to make the overall molecules go more rapid, more rapid. You have a very high pressure system at that point. Okay? And then we're even going to make it more pressure because we're going to do work by pushing this piston down. Okay? That's the part I didn't tell you on the first time through. We're going to push this piston down, just like here. We're going to compress it, give it even more high pressure, and force it out of the actual inside of the refrigerator. Okay? At that point, you have something that has a relatively high temperature, the refrigerant, and then something that has a cooler temperature, which is now outside the refrigerator. So thermodynamics tells us that the heat transfer will go hot to cold. Okay? Heat energy is going to go from the refrigerant outside. So that's going to move. And then you're going to essentially become a liquid. That refrigerant is going to become a liquid because you're losing that energy. Okay? And then it comes back down and it turns this little expansion valve, and then only bits and pieces of that liquid will go through at a time. Okay, a lower pressure liquid goes back into the refrigerator. Okay, that's how a refrigerator works. It uses the work right here, the expansion work, or sorry, the compression. It uses that work to do heat. And what I mean is that it's essentially heating up the exterior, right?
Oh, so
It's not heating up inside of that refrigerator. It's heating up that exterior, moving that heat from inside to outside.
so that's why the back of the refrigerator be hot sometimes?
Yes, that's exactly right, because you are moving that energy from the pipes that are inside to the pipes that are outside. Okay? So you're using work to do heat. That is a refrigerator. If you use heat to do work, that is a heat engine. Okay? I guarantee I'm going to answer. Yeah, what's a heat engine? What's a refrigerator? Okay? Those are the answers. Don't say the refrigerator is what I pull my food out of the heat. Okay?
So wait, what was the question?
What is a heat engine? What is a refrigerator? Okay? So what do you use it for? One to do work to become heat. One from heat to do work. Go get those backwards. Okay? Sound good? Alright. Was refrigerators more thrilling than you thought?
No.
No? That's all it's interesting. These are your symbols, and whether or not they are positives or negatives. I turned off my own. Oh, there. I printed off your slide number 13 so that I can look at it. Okay? So I'm going to look at slide 13 and go through the process. If you would like to look at slide 13, that's also probably pretty good. I'd imagine that would be top of page 3. I'd imagine. I don't know that for a fact.
Yeah,
Is it?
because it's like 6
I would
slides
imagine,
on
yeah.
each page, so.
Yep. Top left. Okay? So, let's go ahead and go through what's happening, what's really happening in this refrigerator in terms of energy transfer, internal energy, so heat transfer, work, and then internal energy. Okay? What does Q mean? Do I have to know that? What does Q mean? No? Q.
That means
Heat.
quantity.
Okay? Heat energy. That is going to be absorbed or released from the system to the environment, vice versa. W means work. That was the easy one, right? And delta U is internal energy. You're absolutely correct. So first thing we have to know what all three mean. Okay? And then we're going to explain the process a little bit. So here is your A. So this is after the expansion valve. Okay, so we're going to start at when it's a refrigerant and it's low pressure liquid. So this is A. And then what you have is that energy is going from inside of that refrigerator to the system, right? The refrigerant is the system. So you're going to environment to the system. So your heat, if you look at it, it says Q is greater than 0 when energy is added to the system as heat. So that's what's happening. Energy is added to the system as heat. So Q is positive. Okay? The amount of work done in that one is 0. You're not doing any work when you go through from a liquid to a gas. You're not doing any work. So if you use your equation, which is delta U, internal energy equals Q minus W. That's the first law of thermodynamics. If you use that, you'll realize, hey, delta U must be positive if Q is positive and W is 0. Okay? That's how we get the internal energy, is by just plugging in. If this is positive and this is 0, then delta U must be positive.